This is the fourth and final video of a series where I try to show you how to analyze problems associated with psychrometrics. In other words, atmospheric air, where we've got a mixture of dry air and water vapor together in commonly observed processes that we encounter in our daily lives. And so what I want to do and show you on this one is basically how to analyze a whole house air conditioning system for the summer. And this is going to be a schematic of what we're going to analyze with a little bit of a crash course in between. Okay. Residential air handler crash course. This is a quick repeat from the third in the series because I've already presented these slides for winter heating of a whole house HVAC system. And then our analysis, our example problem is going to be for home air conditioning for the summer. Okay, and so this is a schematic of a basic home residential HVAC, heating, ventilating, and air conditioning air handling system, which has the ability to heat in the winter, covered in the third video, and to cool in the summer. And so this is what we're going to focus on this video, where we've got the evaporator section from a traditional refrigeration vapor compression cycle that's rejecting heat from the warm return air coming from the rooms, and it's cooling it way down, and it's supply air going back to our rooms to make us nice and comfortable. And the other thing we see in the summer here is that we've got this drip, drip, drip of cool water that's going down to the drain, okay? And we'll talk about more. That really makes it a little more complex. And so I do want to let you know that this the cooling analysis is more complex than the heating analysis, but you're going to be able to get through it. So if you can follow along the example problem, you'll have something to go by. You can download the static slides, and that'll give you a starting point when you have your own analysis to perform. Here's the video of the real equipment in our own Daleville home. Return air coming from the rooms into a blower section. The blower is blowing air. We go 180-degree turn, blowing air up through the heating, and then for the summer cooling section, here's this PVC pipe that is that drip, drip, drip in the summertime, where we're really cooling the air down, the return air down, and we're condensing cool water out of that mixture, and then down we go to the floor drain. Now let's look at the TS diagram that is different than the heating situation. We're going to be coming into our air handler, again, at a low partial pressure. That's why we're low on the TS diagram. Remember, this TS diagram is only looking at the H2O vapor in the air. This diagram does nothing associated with the dry air. That's a whole different situation. But we're starting here at our return air temperature coming into the air handler at a low partial pressure, PV1. We're going to be cooling it down across that evaporator coil, and we're going to cool it and cool it and cool it down at constant partial pressure until we hit the dew point. Now, if we have enough cooling capacity to cool below the dew point, let's say our supply air then going back to our rooms is below the dew point, then our process line takes a little dog leg here, and so it follows left to right at 100% relative humidity at variable PG with decreasing temperature until here's the final partial pressure at the supply air temperature. And in fact, our cold condensate, that would represent our cold condensate, because condensate is a saturated liquid at the supply air, at the cooled temperature. So this would be the state of our cool condensate. So that is different than the heating situation. Please be aware of that in your own analysis. And so here's our example. Now it's going to be familiar because it's based on the third video. Field measurements conducted on a residential home air conditioning system. The return air duct going into the air handler measures 61 by 61 centimeters. I measured it myself. And the average inlet air flow velocity is 122 meters per minute. Measured it myself. And coming back at 24 degrees C and a relative humidity of 50%. That's very typical of the summer. And the system pressure here in Daleville, atmospheric pressure about 100 kPa. Okay. The inlet air then is cooled down in the air handler and supplied back to the rooms at a temperature of 11 degrees C. So that's very typical. Okay. Now look at this assignment. The assignment is longer than the given information. Let's go through what we've got to calculate for our air conditioner analysis. The volumetric flow rate entering the air handler. That should be easy. Determine the dry air mass flow rate entering the air handler. Now recognize that will also, the dry air mass flow is going to exactly equal what's leaving the air handler. In other words, the supply air back to the rooms. However, determine the water vapor mass flow entering the air handler. Let's think about this. And then the relative humidity of the moist air going back to the rooms. We're going to be able to find that. Now, you're going to be able to see with your eyes. If you can watch this in the summer, you can see if any vapor is condensed from the mixture and flows to the drain. You just watch the drain. If you see drip, 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 that tells you that the vapor going back to the rooms will be less than what's coming into the air handler. So that's a verbal statement of continuity for the H2O, water and vapor. Okay. So if condensate is produced, determine its temperature and the mass flow rate of the drip, drip, drip. Determine the rate at which heat is rejected from the return air. Now that's for the design of your air conditioning system. And determine the cooling effect in tons of cooling. That's just going to be a conversion factor. So this is very much of a real world problem. I want to take you through step by step to show you how to analyze this situation. This is the way I measured the average flow velocity going into the return air duct. Set up a vane anemometer in front of the inlet duct, measured the inlet duct, measured the velocity, average velocity with the vane anemometer to be 122 meters per minute, 24 degrees C, relative humidity 50%. Here's a repeat image of our air handler showing only the cooling situation. Let's start with a sketch. Here, I've labeled this state 1, return air from the room, state 1. Then here's our evaporator coil. This is where heat is rejected from the air. To state 2, cooling supply air going back to the rooms at 11 degrees C. Okay, so let's see, state 1, I forgot to read this off. 24 degrees C at state 1 and 50% relative humidity at state 1. Okay, so in the summer, it is common to observe dripping cool condensate dripping out of the evaporator section and dripping into the floor drain. You can see it with your eyes. Easy, let's do the easy part first, the volumetric flow rate. We've got the average velocity, we have the area, so it's a simple matter to say the area times the velocity is the volumetric flow rate of 45.4 cubic meters per minute. Okay, so at least we've got one thing on the check box. We've got some partial credit so far. The next thing we want to do is go to state 1 and 2 and gather some properties. Okay, and so state 1, this is the return air. This is the hot air coming back from the rooms, 24 degrees C. We will write down P sub G. P sub G is 2.985 kPa. Okay, bars, kPa, 2.985 kPa. Another thing we'll do, we'll look ahead. We know we're going to have to use the first law to determine the heat transfer rate. So let us look at, now I've circled the wrong thing here on my slide. I should have circled 2545.4 I circled the wrong enthalpy value. So Hg1 is 2545.4. Gosh, I hope I logged the correct number. Now, at the cool air, the supply air back to the rooms, the P sub G is 1.3 kPa. And in case we're below the dew point, I'm going to write down H sub F 46.2. And we know that we're going to need H sub G 2521.6 kilojoules per kilogram. So please excuse me for circling the wrong H sub G down here for my return air. Okay. All right. So what we're going to do here is let's get our partial pressures at state 1 first. And that's going to enable us to get moving. All right. So we wrote down PG1, 2.985 kPa, 50% relative humidity. So PV1, the partial pressure of the vapor, 1.49 kPa. So then we'll immediately calculate the partial pressure of the dry air. We'll take the system pressure, 100 kPa, minus 1.4925 to give us almost 100, 98.5 kPa is the partial pressure of the dry air. Okay, next. The humidity ratio is going to give us the mass flow of the vapor, and then we're also going to be able to get the dry air mass flow coming in at state 1. Let's see. The first thing to do, use the ideal gas equation of state to get the specific volume of the dry air. Use the partial pressure of the dry air to get the specific volume of the dry air. That's Dalton's model. So P of the dry air, 98.5. R for air, you should know by heart, 0.287 kilojoules per kilogram degree K. T1, 297 degrees K, absolute temperature. It's going to give us a specific volume of 0.8653 cubic meters per kilogram. Now, we've got the volumetric flow. We just calculated that, 45.4. So the volumetric flow divided by the specific volume of the dry air. Look at those units. Look at the units with your eyes. Okay. That's what gives you the mass flow rate of the dry air, 52.46 kilograms per minute. We'll use the humidity ratio at state 1. Let's see, that's going to be, how did we get the humidity ratio? It's going to be 0.622 times the PV1 divided by the quantity, P system minus PV up here. I wrote it down up here. Okay. P system minus PV, well, that's just the partial pressure of the dry air. Okay. So that's the way we compute omega 1, the humidity ratio at state 1. So we got m dot of the dry air. We multiply it by the humidity ratio. We check our units. Yep, that's going to come out to be m dot of the vapor is 0.4944 kilograms per minute of vapor flowing into the air handler. Okay, so we've got 2 more things to check off our list of analysis. We've got the dry air mass flow coming in and the vapor flow coming in. Now, remember, going out, the dry air flow, think of the continuity equation. There's no place else for the dry air to go other than out. So those two have got to be exactly equal. The dry air flow in and out must be the same. Not so on the vapor. Okay, let's check the dew point. How will we check the dew point of state 1? Well, we wrote down the partial pressure of the vapor, 1.493. We remember the definition of dew point, that if we cool the mixture at constant humidity ratio or constant partial pressure, it's the same thing. Whatever temperature we get, where PV equals PG, here's PG, saturation pressure, that's the dew point. Okay, so we got 1.493 at state 1 for partial pressure, PV1. So let's shop around in our column, in our temperature table. Well, it's almost an exact match with 13 degrees C. And so the dew point temperature here is going to be a little shy of 13 degrees C. And we're cooling our mixture down to 11 degrees C. We are cooling our mixture below the dew point. So right there, we don't have to do any more calculations to know that we're going to get a cool drip, drip, drip of condensate going to the drain because we're cooling our mixture below the dew point. That's an important technical thing to observe, more than just blindly going through the calculations. Okay, but let's do the math now. So I went in and I copied down my PG values and temperature values from the temperature table to determine that the dew point is 12.95 degrees C, just about 13. We observe then we're cooling below the dew point. Okay, so yes, it's below the dew point. And so immediately, our immediate conclusion is, go back and think about that TS diagram. Our partial pressure at state 2 is in fact PG. So therefore, the relative humidity of the air going back into our rooms, the cool air, is going to have a relative humidity of 100%. That is moist air going back into our rooms. Okay, very important conclusion. Okay, supply air will be saturated with vapor. In other words, 100% relative humidity. Big conclusion and an answer to the questions that were asked on our analysis. Now let's move ahead. And so we're going to be able to, now we know m dot of the dry air going out. If we can get the humidity ratio, kilograms of vapor per kilogram of dry air, then we've got the mass flow of vapor going out in the duct. So let's calculate omega 2, the humidity ratio at state 2. Well, PV equals PG at 11 degrees C. We just looked it up, 1.312. Okay, at 11 degrees, PV is at 1.312. That's the saturation partial pressure, 100% relative humidity. Okay, and so what we do, we'll apply the definition of humidity ratio using our partial pressures to get omega 2 is 0.00827 kilograms per vapor per kilogram of dry air. We're moving along. So now we can get m dot of the vapor at 2. We've got m dot of the dry air, just like the inlet. Apply omega, 52.46 times 0.00827 equals 0.43382 kilograms per minute of vapor leaving in the duct. But let's compare that to what was coming in with the duct. Wow, 0.49. They're both kind of small numbers, but there is a difference. Well, the difference is what's dripping to the drain, m dot of the condensate. It's the continuity equation. Okay, so we simply take the difference of these two numbers to get what's dripping to the drain. Condensate is 0.0606 kilograms per minute. That'll tell us the drip, drip, drip flow. So we've answered another question in our list of things we needed to analyze. All right. Now we're down to a hard part. Okay. How much heat are we rejecting from this air vapor mixture? Well, we're going to use the first law. Use the first law. When in doubt, use the first law. Energy balance. Okay. I didn't even write it on the slide because in the third video we covered W dot. What's W dot for this process of cooling the air? It's 0. There's no shaft coming into or out of the cooling section. Okay. The cooling section, the evaporator is not lifting a weight. So only heat Q on the left-hand side, Q dot in minus W dot out, well, that's 0, equals M dot of the dry air times enthalpy out minus enthalpy in plus M dot of the vapor at 2 and 1 plus M dot of the condensate. Okay. Now, I do see that I was a little fast and loose here. M dot of the vapor is not constant, is it? Wow. So I've made a little, so make a mental note. this has got to be m dot of the vapor at 2, H2 of the vapor, minus m dot of the vapor at 1, H1 of the vapor. Okay, so this is a typo. This is a careless error that I wrote out. But magically, I corrected it down here in the bottom line. So let's see. So I'm going to have to apologize for this. Not m dot of the vapor is not constant. So I should, over here in this term, I should have m dot vapor 2 times H2 vapor minus m dot vapor 2, 1, H1 vapor. All right. How do we simplify and get things straightened out? Well, we've got Q dot N equals m dot dry air. We've got it. Air is an ideal gas, and for this small change in temperature, delta H is Cp times delta T. So we need Cp of air. We've got delta T of air. That's given. Now, here's where I made my correction. I've got m dot dry air times omega 2. That would be m dot of the vapor at state 2, okay, Hg2, minus m dot of the dry air times omega 1, Hg1. Okay, so I have gotten the correction. I have fixed my typing blunder. I've still got to calculate. So let's see. I've got condensate leaving. I've got to compensate for that too. So in my first law, I've got to add a little term here. And I think I didn't mention that up here. Again, sorry. Okay. So plus, I've got m dot of the condensate, HF of the condensate. It's leaving. That's why I've got a plus sign here. Now, there's no condensate coming into the system, is there? That's why it's not a delta. And then how did I come up? What is m dot of the condensate? Well, I recognize that I'm using the continuity equation. So this is simply the difference between omega 1 and omega 2, a larger number, a smaller number. So the difference in vapor flows is the condensate flow. So I'm sorry that I didn't take step by step by step by step going through here. I will endeavor to fix this slide, and you can download the static slides, and I will promise to have this fixed up in the static slides. So please excuse that. All right. So anyway, this is a term that needs to be included. It is an outflow. So let's think about, without going back in the slides, let's think about our system. We've got an inlet, one inlet, and we have two outlets, right? We've got the air vapor mixture going to the rooms, and we've also got an outlet, drip, drip, drip to the condensate. So that's what this term is all about, the drip, drip, drip to the condensate. So this is correct. This is correct. And I will endeavor to go fix my static slide before I post these, the correction. Okay. So this is the setup for how we get the heat added. It had darn well better be a negative number, right? So the heat added is going to be a negative number because we're rejecting heat from the air. We need to go get C sub P for air. We'll go to table A20 and we'll write down C sub P is 1.005 at nominally 300 degrees K. This is common practice to use CP equals 1.005 for air for heating, ventilating, and air conditioning problems. Okay, so now, again, please excuse my blunder, but I've gotten things straightened out here. Q dot N is equal to m dot of dry air times the enthalpy change of the dry air plus m dot of the vapor at 2 times enthalpy at 2 minus m dot of the vapor at 1, H1, okay? And then finally, the last term, plus the condensate flow, which is m dot of dry air, omega 1 minus omega 2. That's the continuity equation, times HF2, a small number. HF is going to be a little number, but we're going to include it in. Okay, and so here we've got our, we've logged all our data. We've logged our enthalpy values. And I see that I have correctly logged my enthalpy value despite my incorrect circling of HFG. Okay, I've correctly done HG2. I've logged HF2. That's the enthalpy of saturated liquid. This is the condensate enthalpy. This is the vapor enthalpy, 2521.6. Okay, so now it's plug and chug. Here's my first law. So I've got Q dot N equals negative 1412 kilowatts. Oh, notice here, to get units straight, look at my work. I have m dot dry air of 52.46 kilograms per minute. In order to get unit straight of kilowatts, kilojoules per second, I needed to transform my m dot of dry air to kilograms per second. Divide this 52 by 60 to get 0.8744 kilograms per second. Okay, so that's why I try to show these screenshots to see some little details that I may have overlooked in explanation. So Q dot N, negative, makes sense, negative 14 kilowatts. Oops. So I changed this back to kilojoules per minute because in the back of the book, I found a conversion. 211 kilojoules per minute equals 1 ton of cooling. I should have shown the conversion factor in here. I'll try to go back and get a screenshot of that. So please excuse me for these blunders. Okay, 211 kilojoules per minute equals 1 ton of cooling. And so I divide negative 847 by 211 to get 4.02 tons of cooling. And I dropped the negative sign because I said tons of the cooling effect. That's why I was able to drop the minus sign. I didn't say heat added. So 4 tons of cooling. Woo! So that is a complex analysis, and here is the summary. All right, so that's example 1. How would we solve this exact same problem using the psychrometric chart? Now, the advantage is it's going to go much faster because it's not so much tedious computations. But you've got to have that practice working with the psychrometric chart. So let me work you through how to solve this problem using the psychrometric chart, and then we'll compare. Exact same problem. Okay, so let's plan our work. So first thing we've got to do is locate states 1 and 2 on the psychrometric chart. That'll be fairly easy. Okay. Determine state 1's specific volume. So that's what we're going to need to get the flow rate of kilograms per second of dry air. Then we're going to determine the relative state 2 relative to the dew point. So we're going to be able to visually look at the dew point. Then we're going to determine the humidity ratios for states 1 and 2. We will discover that they are different humidity ratios. And then we're going to look at the moist air enthalpy for states 1 and 2. So convenient because look at this sort of diagonal axis on the psychrometric, specific enthalpy of moist air. So the nice thing about this scale is that it jumbles in enthalpy for the air and vapor mixtures, making it much, much easier to deal with. So be aware of that. And then here, so x-axis, the dry bulb temperature. That's the given temperature measured with a thermometer. There's the dry bulb. Y-axis, humidity ratio, kilograms of water per kilograms of H2O vapor per kilogram of dry air. And then also we've also got axes called specific volume, cubic meters per kilogram of dry air. Okay, we've got some lines there. And we've also got relative humidity curves, 10, 20, 30, 40, 50, 60. Pretty complex. All right, so let's locate states 1 and 2. State 1, given. We've got 24 degrees C coming into the air handler at 50% relative humidity. Just put a big black dot there. We will start cooling our mixture so that air is passing across the cold evaporator, and it starts cooling at constant humidity ratio until it hits the dew point. And sure enough, now look, we're cooling down to 11 degrees C. Well, look at the dew point temperature. The way we measure the dew point temperature is over here where it says wet bulb or saturation temperature. So you can see with your eyes here that we're about 13 degrees C. 13 degrees C is the dew point here, okay? Once we hit the dew point temperature, we continue to cool and cool and cool until we reach 11 degrees dry bulb temperature. So here, we come down here at 100% relative humidity until we intersect 11 degrees C on the x-axis. So there's our second point right there. There's state 2. All right. I hope you understand that. Next is, how do we get the specific volume at state 1? Well, here's our dot. Okay. We look, we have to move our eyes. Specific volume. Here's 0.9 specific volume. Here's 0.85, and here's 0.8. So we're a little above 0.85, and we're below 0.86. And so we have to use our calibrated eyeballs to about 0.855. We'll see what I logged here in a couple of slides, but looks like about 0.855. Humidity ratios. Well, let's go read across state 1, vertically across. We'll read across this humidity ratio. And then sure enough, we're cooling below the dew point. So we've got a drip, drip, drip of condensate. Our humidity ratio at state 2, therefore, will be lower. So we're going to come all the way across it. Here's state 2, come all the way back across here to a lower humidity ratio. And we'll write those down. Finally, looking ahead, we're going to need to apply the first law. So we will read the specific enthalpy, little h, kilojoules per kilogram of dry air. We're going to read both of those off with these diagonal axes. And so it looks like state 1 is going to have an enthalpy of about, looks like about 48. And state 2 looks like about 32, little h. All right, let's see what I logged. All right, so we've got omega-1, these little check marks, what I logged from the psychrometric chart, omega-1, 0.0081. I'm sorry, omega-1, a bigger number, 0.0095. Omega-2, a smaller number, 0.0081. V1, 0.855. Okay. H1, 48. H2, 31, all in both of these H values in kilojoules per kilogram of dry air. Okay. And then, of course, here's the computation of the volumetric flow rate that we've already done. Okay, so all these values, all these numbers I've been able to log from the psychrometric chart, and the rest is going to be pretty easy. So the computation is not so involved. M dot of dry air. We got, it's simply going to be the volumetric flow rate divided by specific volume, 53.09 kilograms per minute of dry air at the inlet and the outlet. At state 1, the vapor coming in, I got omega-1, kilograms of vapor per kilogram of dry air. I've got m dot of the dry air, so therefore multiply these two together to get m dot of the vapor at state 1, 0.5044. Same idea at state 2. I got a new value of humidity ratio, a lower number, same dry airflow. So m dot of the vapor at 2 is 0.4301. So by subtraction, I've got this much vapor coming in, this much vapor leaving. So by subtraction, continuity equation, what's the condensate, the drip, drip, drip is going to be the difference between those two, 0.0743 kilograms per minute. Now, the first law with the psychrometric chart, it's easy. The first law, Q dot in minus W dot out, that's 0, equals m dot of the dry air times H2 of the moist mixture minus H1 of the moist mixture. Just subtract two numbers from each other, okay, to get Q dot in is negative 15.04 change that to kilojoules per minute. So I would multiply 15 by 60 to get 902 kilojoules per minute. And then my conversion to 11 kilojoules per minute is a ton of cooling. So my cooling effect is 4.28 tons of cooling for this situation. All right. And here's the results. Let's compare. Let's compare the two methods for exactly the same problem. We used the property table, a lot of complex computations. Okay. You can see with your eyes what we've got. We use the psychrometric chart for exactly the same problem. You can see with your eyes. Here's what we've got. And I find it to be extraordinarily interesting that we get functionally, practically the same result using either method. Now, not exactly the same, not to 4 significant figures. We don't get an exact match. There's no reason to expect an exact match because your calibrated eye just can't get 4 significant figures from that graphical chart, right? So here's the key, here's the takeaways from this example problem. You should understand how whole house heating and cooling works. What are the differences? What are the similarities? For the summer air conditioning mode, when you're cooling air, you've got to check the dew point temperature against what you're cooling it to. That's a must. When you're below, the relative humidity increases a lot when you're cooling, and it might even be 100% relative humidity that you're sending back to the room. Okay. You will apply the continuity equation and the first law to determine the cooling effect. That was that complex first law statement when we were using the steam tables. Okay. And the psychrometric chart gives you 3 significant figures at most, but it gives you good, adequate results for engineering design when you're designing heating, ventilating, and air conditioning systems. So this is terrific. I hope that you have gotten something out of all 4 of these videos. Now, I've got to apologize for my slide blunder in that statement of the first law. Once we adjourn here, I'm going to go and I'm going to fix that slide. And so, of course, it won't show up on the video, but I'm going to fix that slide before posting it as static slides to the website. Okay, I hope you've gotten something out of these videos. I hope you will use these example problems to get experience on your own. I want you to get experience working through these problems on your own to prepare yourselves well for quizzes and tests and exam problems. I can predict that you will be given a psychrometric chart problem on a test or an exam. That's my prediction. So really want to encourage you to learn how to use the psychrometric chart.